Let's look at the next question. Yeah, this one's similar, but this time for the worst case. Worst case. Worst case, the formula, when we merge M array and B array, not B, N array, the formula is M plus N minus 1. Okay? The total number of elements, M plus N minus 1. That's the worst case formula. All right. Here, look at these four options. A less than B, B less than C. Yeah. First, let's look at which one is the smallest among the four. Yeah. They have similar structure, but let's look at which one is the smallest. Right? Yeah. Constant part the same. Constant part the same. The coefficient part, 2, 2, 2, but one of the variables coefficient is 1. The remaining 2. Yeah, that kind of structure. Okay, 2, 2, 2. So definitely it's not the smallest. We want to find the smallest. Okay, yeah. All right, smallest. This is smallest. Can you see that? This is the smallest. 2, 2, 2. But the coefficient 1, that variable is the largest here. The largest one we only multiply once. Okay? Yeah. This is not the smallest. All right. Or, all right, in another way. Yeah, let me show you in another way. Because the constant part is the same, so when we do comparison, we can ignore the constant part, right? They all have minus 2 constant part. We can ignore that. All right. Then, when we compare which one is smaller, A, can we write 2A plus 2A plus 2B plus 2C minus A. How about that? Okay? All right. B, same 2A plus 2B plus 2C minus C. Okay? All right. C, 2A plus 2B plus 2C minus B. Okay? D, no minus. Okay? 2A plus 2B plus 2C. That's it. Okay? So definitely the smallest one comes from one of the 3 expressions. Which one is smallest? This one is smallest. Because you minus the largest number. Same number, the parenthesis number, same in these 3 options, but this one, you minus the largest number here. Okay? Yeah. So option B is the smallest one, but we don't know if we can achieve that or not, right? Yeah. Can we make this? If we can make it, then that's our answer. If we cannot make it, we need to find the smallest one from the remaining options, because we cannot make it. All right? Let's just try to make it. Okay? Then it will be our answer. Okay? All right. So let's do our work to make that happen. Okay? Yeah. So that's the work part. Okay? Yeah. Merge. When we merge, yeah. So let me just write as simple as possible. Okay? That's it. Yeah. All right. Let's merge A array and B array. Okay, so we get, by the formula, number of comparisons, A plus B minus 1. Okay, the number of elements, A plus B. Okay, yeah. All right. Hey, sorry, minus 1, not minus C. Yeah, minus 1. Okay, all right. Comparison. Then, next step, merge C array and A plus B array. Number of comparisons, total elements, A plus B plus C minus 1. Number of elements, A plus B plus C. Okay? Then, the answer for this case, A plus B minus 1 plus A plus B plus C minus 1. Okay? Equals 2A plus 2B plus 1C minus 2. Yeah, you can see we make it. In this way, we make it. Yeah, so that's the answer. That's the smallest option, and we can make it. Yeah. That's all we need. Yeah. Okay. All right, so that's this question. Yeah. It's the worst case. So you can see best case, worst case, the difference. Yeah. Formula is different. Yeah. All right. All right. Yeah, this one. Yeah. This one is designed to check our understanding on average case efficiency. Here, another binary search example, but this one, we put a restriction. All right, yeah, so let me read the statement first, then we do some analysis. We apply the binary search on a 15-element array. First, you look at the 15. This is a special number, power of 2 minus 1, right? Yeah. First, from this 15, it's a special number, power of 2, 2 to the 4th, minus 1. Yeah, that means this binary tree is a complete binary tree. Okay, the first thing we observe. All right, assume that a given key appears in the array. Yeah, you can find it. And it is between the 5th element and 12th element inclusive. All right. How many comparisons do we need for the average case efficiency? Yeah. Average case, we need to take average of all the possible cases. The cases we will see between 5th element and the 12th element inclusive. Yeah. So that is the condition we have. All right. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? Yeah. But the cases we need to consider inclusive between, yeah, look at these cases. Start from 5th, only consider these cases. And we do not need to consider 1, 2, 3, 4, 13, 14, 15. Then we take average of the number of comparisons. Yeah. All right. First, let us count how many cases do we have. Okay? Yeah. How many cases? 8, right? Yeah. Yeah. 8 cases. That means denominator is 8. Denominator is 8. Now we need to figure out the numerator. Yeah. All right. Let us draw the complete binary tree. Complete binary tree. When we draw, let us put number there, right? Yeah. 8 first, right? After 8, 5 here, right? 8, so here, 12, right? Right? Yeah. So the first one, 8. After that, is it 5? Sorry, 4, right? Yeah. All right. 4, not okay. And here, 12. Yeah. So 4 here. 12. 4, that 2, 6, 10, 14. All right. Then 1, 3, 5, 7, 9, 11, 13, 15. All right, yeah. All right. The cases we need to consider. The cases we need to consider. K between 5 and 12. Okay? Yeah. All right. 8, 1 comparison. All right. 4 and 2, but 4 and 12, 12 corresponds to 2 comparisons. Okay. 6, 10, 14, these 3 corresponds to 3 comparisons. Okay. Number 5, 7, 9, 11, these 4 comparisons. All right. All right. So let's do the numerator. 1 comparison, we only have 1 node in the range. All right. 2 comparison, we have also 1 node, 12 in that range. 3 comparison, how many nodes? 3 nodes in the range. Okay, 6, 10, 14, yeah, in the range. 4 comparison, 4 in the range. Okay, is that correct? Yeah, because 1, 1, 3, 4, we have 9. We have 9 elements. Is that correct? But we count only 8 cases. All right. So 8, 1 comparison, 12, 2 comparisons, 6, 10, 14, 5, 7, 9, 11. Yeah. Why it is wrong? Is that wrong? Yeah. Over 8. The question is 9 or 8. Here it looks like we have 9 cases. 1, 2, 3, 4, 5, yeah, 8 cases. Why here we get 9 cases? 1, 2, plus these 3, so that's 5 and 4 more. Can you see anything wrong? Yeah. So 8, 12, 6, 10, 14, 5, 5, 7, 9, 11. Yeah, nothing is wrong. Yeah, that's strange, right? Yeah. Let's see. Let's see. Oh, 14. All right. Yeah. Oh, good. Thank you, Fuke. Yeah. Fuke telling us, yeah, 14, check it. Yeah. All right. Okay. Thank you, Fuke. Yeah. Remove 14. All right. Remove 14. That means 3 comparison, we only have 2. Yes. All right. Yeah. So, okay. Yeah, that's the expression. All right. Yeah, you do not need to calculate. Yeah, the answer we can calculate easily. So 3, 9, 16, 25 over 8. Yeah. All right. Yeah. So you can see for special cases like this, then we take average in this way. Think about that. Okay? Yeah. This helps us understand the average case efficiency, how to calculate. Yeah. Because when I grade that example, yeah, our homework exam, midterm test, yeah, that's midterm test. That example, many of you couldn't answer this one. So I think I will give you a similar question in the final. Similar, okay? Yeah. So I change the numbers, but you need to go through this procedure. Yeah. But at that time, you can use this diagram to help you go through, yeah, understand. Yeah. I may not give you a complete binary tree. Yeah, here 15, so you have a complete binary tree. But I may give you, different binary tree. Yeah. But you'll figure out in the similar way. Yeah. All right. Yeah. So that's this question. The next one, yeah, let's look at this. Yeah, we did a similar one in our midterm, yeah. But this one, let me just repeat this question another time. Given a 10 elements array, it is known that x1 is not the smallest element, and x10 is not the largest element. Okay? Yeah. It is known x1 is not the smallest, and x10 is not the largest. Okay? Yeah. What is the minimum number of comparisons we need to find an element that is neither the largest nor the smallest for the worst case? Minimum. Yeah. X1 is not a minimum. Yeah. First, yeah, here we need a minimum number of comparisons to find an element that is not a minimum. Yeah. All right. So now we need to find some xj not the minimum and xj not the max. Okay? Yeah. Now, all right. First, you cannot use x1 we know not the minimum. All right. But, yeah, it's possible. You can consider x1 and x10. Yeah. Any element you can consider here. All right. So here the minimum number of, not the max, not the minimum. All right. All right. Yeah. So this question a little tricky. Okay. Yeah. All right. First, let's think in this way. First, yeah, let's do not consider the condition given here. That's the condition given here. Okay? Yeah. First, let's ignore this condition. All right? So given 10 element array, how to find an element that is not the maximum, not the minimum? Yeah. First, let's solve that one. Okay? That should be simpler than this one. Okay? Not the maximum, not the minimum. All right. In that one, can we select 3 elements in that one? 3 elements. Okay? Yeah. 3 elements. Then find the median. With 3 comparisons. Okay? We know we find the median of 3 elements. We need 3 comparisons. That median will satisfy that condition. Okay? The median will satisfy that condition. Median. Because the median cannot be the minimum, right? And the median cannot be the maximum. Yeah. All right. So you can see the worst we can do is 3 comparisons. Because we do not consider the given condition, x1 not the minimum, x10 not the maximum. We do not consider the given condition. We need a minimum 3 comparisons. So the only thing, so now we need to do better than 3 comparisons. With the given condition, we need to do better than 3 comparisons. Yeah. So our goal here better than 3 comparisons. Okay, all right. Yeah. Can we use 1 or 2? All right, I'll admit. Can we use 1 or 2? All right. Comparison to find the answer there. So here in your mind, your target, 1 or 2. Yeah. Is 1 possible? If not possible, 2. Yeah. But not 3. Yeah. Yeah. 3, we make it here. Yeah. All right. Okay. Just pick arbitrary element. All right, pick arbitrary, compare it with x1. Yeah. Let's say compare x2 and x1. And look at the cases. we only have two cases. We can assume they are different. x2 less than x1 and x2 greater than x1. Okay? Yeah. If x2 less than x1, all right. If x2 greater than x1, yeah, that's x2 less than x1. Yeah. All right. Let's see. x2. We know x1 is not the minimum. Okay. Yeah. x2. All right. Let's see. x2 less than x1. That means x2 not the maximum. Okay. Yeah. x2 not the maximum. Okay? Yeah. If x2 greater than x1, what can we get? What can we get? Can we get x1 not the maximum and x1 is the choice? How about that? Because we already know x1 is not the minimum. We just take x1. x1 not the minimum, not the max. So for the second case, one comparison will do it. Okay? So for the second case, we just need one comparison. How about that? One comparison. Okay? All right. For the first case, x2 not the max, but we don't know x2 is the minimum or not, right? We don't know x2 is the minimum or not. Okay? Now let us compare x2 and x10. Okay? Yeah. x2 and x10, we know they're both not the maximum, right? Yeah. Because this is a continuation of the case 1. This is the continuation of case 1. This case. Continuation. Okay? So we know they both not the maximum. So the larger one is not the minimum. How about that? The larger one is not the minimum, and it is the choice. How about that? How about that? Yeah. None of them is maximum, all right? Given condition and the first case, right? None of them is the maximum. But we don't want the minimum, so we take the larger one of the comparison. The larger one cannot be the minimum, so either x2 or x10, so that is our answer. How about that? Okay, yeah. So here, this is a good example. How do I design a challenging question like this one? Now, this will be one of our possible, here I give you the question style you may have in the final. Yeah. Part B, yeah. Part B, can you solve a question as hard as this one? Not too hard. Okay? If you really work, you know your goal, 1 or 2. You need a 1 or 2 comparison, but not 3. Okay? Never get 3. But 3, we already have it. Without that condition, we already have 3 comparison solution. All right. So now, what do you need? Can you use 1 comparison or 2 comparisons to find the answer? The worst case, 2 comparisons. No. The best case, 1 comparison. So this is so the question style will be similar to this one. Okay? Yeah. Not too hard, yeah, but you need to really do some work. Okay? You really need to do the work like what we are doing here. Yeah. Yeah. All right. This one, because after you take this course, you need to know how to solve this one. Yeah, this is a very challenging question, but otherwise you may not really learn some harder part. Yeah. This one, we did part of it before, yeah, in the example when we work on that 5-element array. We find the median. I got confused. Actually, I work on the case for this one. Yeah. So here, let us complete that solution. Yeah. We complete that solution. First, preparation. That part is simple. Yeah. So here, let me repeat the preparation. x1, x2, our first comparison, the winner, we can say smaller one is the winner, x1, all right? x3, x4, winner, second comparison, x3, okay? Yeah. Third comparison, the winner, let's say x1, comparison number 3, okay? So that's the preparation step. All right, yeah. After that, we have that diagram like this. x1, x3, x4, x2. Now, x5, when we need to get a 5, x5 to do the comparison, we compare it with the middle one, x3, that's the comparison number 4. Okay? Then we have two possible cases. Yeah. The first case, greater than x3. So it's like this. x1, x5, x2, x4, okay? The second case, less than x3. x1, x3, x4, x2, x5 is here. Okay? All right. All right. Then, for this case, it should be a little easier. Yeah. Yeah, let's work on the easier case first. All right. Easier case because let us do comparison. x4 and 5, that is number 5 comparison. Because after we do comparison x4 and x5, we get a 4-element sorted. 1, 3, 4, 5. These 4 elements sorted. Okay? Yeah. 5 comparison. So we will get x1, x3. Yeah. Let us assume x4 and x5. Yeah. If we switch x5 and 4, it's not important. Okay? Yeah. And x2 is here, and we already know x2 less than x1. So when we want to insert x2 into the sorted array, we should compare in the middle with the remaining elements, right? Yeah. So compare x2 with the middle one, x4, that's comparison number 6. Okay? Then after that, you just need one more comparison to get it sorted. Okay? Either x3 or x5, one more. Okay? But not both. You only do one comparison, either with x3 or x5. That's number 7. Okay? So you get it sorted. Okay? Yeah. So x2, to do the insertion, you need 2 comparisons to get it inserted. Yeah, because it's below x1. Yeah. You only need to insert somewhere in that remaining 3 elements. Yeah. All right. All right. So then the top case. Yeah. Top case. Yeah. Actually, the top case is not too much harder. Yeah. Top case. Can you do comparison with x1 and x5? Yeah. Do one comparison, x1 and x5 as your 5th comparison. Yeah. All right. After that, x5 could be higher than x1 or lower than x1. The higher, you need fewer comparisons. Yeah, because you only need to do x2 with x3 and x4. So 2 more comparisons. Yeah. All right. So here, the worst case corresponds to worst case. Although you can consider another case. The worst case corresponds to x1, x5, x3, x4, x2, you still insert somewhere in the 3-element array, compare in the middle, 2 more comparisons. Yeah. So compare with x3 first and one of the 2, so 2 more. 2 more, okay? Yeah. Although here I say the worst case, but the other case, yeah, it looks a little better, but actually same number of comparisons. Yeah. Yeah, we can draw the other case. x5, x1, x3, x4, but the x2 is below x1. x2, yeah, here. Then you at the most you do 2 comparisons, right? 2 compare. So 2 more. Here still 2 more. Okay? Still 2 more. So in any of these cases, after comparison 5, you need 2 more. So the total 7 comparisons. Total 7 comparisons. Okay? Yeah. Yeah. This one is the most difficult question for our class. Yeah. Yeah. So we will not do harder than this one. Yeah. This is the, farthest point we can reach. Okay. We will not go further than this point. Yeah. It's already, that's the boundary of this course. Yeah. Yeah, we won't go further passing this one. But in this one, what do we learn? Yeah, although here the diagram. Yeah, so if you just draw a diagram, yeah, you just write a few words. You do not need to write, complete sentences. Yeah, just make sure I can understand. That's good enough. Okay. So you just tell me what comparison between which 2 elements. That's enough. Okay. All right. So then, show me your flow chart. First step, second step, third step, and what comparisons. Yeah. All right. Yeah. Here, the main thing we learn, all right, when we insert an element in an ordered array, we always do the binary search type insertion. That's the main idea. Do binary search type insertion. Yeah. That's the main lesson we learn from this example. Okay? Yeah. So yeah, how do I, yeah. Insert an element in an ordered array to binary search type insertion. Okay? Yeah. So this is the main lesson we learn from this example. Okay? Yeah. Main lesson we learn from this example. Okay? Yeah. All right. Yeah, all right. Okay. Yeah. Well, I cannot control. Yeah. Let me just use the freezed. All right. Yeah. All right. Yeah. All right. Let us do the last example today. So we will complete this class. All right. So let me just, the remaining about 10 minutes, let us do the last example. All right, yeah, this one. Okay. Find the second smallest element of an array. Yeah. Yeah. Because this example is very useful. Yeah. So we need this background. Find the second smallest element. Yeah. You do not do that way. If you do that, that's not the best solution. You find the minimum element. All right. After that, you remove the minimum element. Then you find the minimum element of the remaining. Although you can solve it in that way, you will get the answer. Yeah. Yeah. I need to change the color. Yeah. All right. Because in that way, find a minimum twice. The first time you find a minimum n minus 1. The second time you find minimum n minus 2. Then you get 2n minus 3. This is not the best solution. Okay? The reason not best solution because the second time when you find a minimum, the second time you didn't take advantage of the information from the first minimum. The first time you do a lot of comparison, but you do not reuse the information from the first round minimum. In that way, you waste a lot of useful information. That's why this way you cannot get the best solution. All right. So how to get the best solution? Here, let me give you the best solution. Yeah. we use the tournament method. Here, there is a special method called a tournament method. Yeah. All right. So players, they play sports game using this kind of tournament method. All right. So let us organize in pairs. Okay. Each round, approximately 1/2 of the players are eliminated. Each round, yeah. People play in pairs. Each round eliminate approximately 1/2 of the players. Yeah. All right, so we're doing this way, okay? Yeah. X1, X2, the first comparison, X3, X4 comparison, and so on. All right? Yeah. X some number, yeah. Yeah. Because based on even or odd, X some number, yeah. All right. So we organize the first round, the second round, and so on. Okay? And the last round, yeah. Last round, the winner, the final winner. The winner, so that the winner, yeah. Find the winner, we need n-1 comparisons. Yeah. Because why n-1? Although when you see this, it's hard to see the total comparison we need to find a winner, but you just think in this way. One comparison, one player eliminated, right? One comparison, exactly one player eliminated. So to find the final winner, n-1 comparisons, players are eliminated. So that way you can see pretty simple. All right. Then the hard part is how to find the second best player. Okay, second best player. Yeah. All right. So second best player. We only need to find the best one in the remaining players, right? Second one equals the best one in the remaining player. Okay? The best one in the remaining players. Yeah, so it's easy to see this one. But the question is, we want to use the minimum number of comparisons to find the best in the remaining players. Minimum number of comparisons. All right. That means if a player loses once to a player other than X1, let's say the winner is X1. Yeah, in order to make the discussion easier, let's say X1 is the winner. All right, yeah. If a player loses, yeah, loses to another player other than X1, then it cannot be the second best. That's easy to see, right? It cannot be the second best. a player loses to another player different from X1. So that one who beats this, the current one, can be considered second best, right? You already lose to a player other than the winner, so you cannot be the second best, okay? Yeah. Then, candidates for the second best. Candidates for the second best. Direct losers. Direct losers to X1. How about that? Only direct losers to X1 can be considered second best. Indirect loser cannot. Direct. So those players who are eliminated by the final winner directly, those players can be considered the second best. How about that? Okay? But how many of those candidates? How many? Because X1 can only eliminate one player at each round. How about that, right? Each round, X1 can only eliminate one player. So the number of candidates equals number of rounds. How about that? Number of rounds. Each round equals number of rounds. And the number of rounds with n elements, seeding function of log base 2 of n. This number of rounds, this is the number of rounds. Okay? Number of rounds. Then, the final answer. Now we are ready to write the final answer. Okay? The first part, get the winner, we need n minus 1 comparison. Okay? The second one, find the best in the remaining player, but we only take the candidates from the direct loser of the winner. That's seeding function log base 2 of n, then minus 1. Yeah, because find the best, you need to do comparison also minus 1. Okay? Then we simplify this formula. M plus seeding function log base 2 of n minus 2. So that is the final formula for the question. For second smallest element, that question, second largest, the same thing, you just apply this formula. Okay? Yeah? Yeah. If I give you just a number, now you can plug in this formula. Okay? Yeah. But how to get it? This tournament method. Okay? Use this tournament method. You can get a solution. Okay? All right. Yeah. So you will see most of the questions in our final will come from these examples. Okay? Yeah. So I change slightly. For part A, I do not do much change. So you pretty much, you can plug in, you can find. But part B, slight, more challenging. I will change a little more, yeah, a little more. So you need to do a little more work. Yeah, just try the best you can. Yeah, yeah. Other than that, and Wednesday still, before the test, I can do some explanation. Yeah, the Wednesday questions, because that's part A, so basically relatively easier questions. Yeah. And I try to make part B questions before I give you part A. So before the test, I can explain a few part B questions in class. Yeah, because that's the best way you can get hints. Yeah, in the class, I explain some of the part B questions. Yeah. So then you just try your best in the last assignment. Yeah. So hope so everyone pass this course. Yeah. Okay. All right, so that's it. Yeah, we use a few more minutes today. Yeah, because we start a few more minutes late. Yeah. Anyway, yeah. This is the last class before the final. Yeah. All right, so that's it.